Welcome to this video about Shellshock Live. Well, Shellshock and coding. Because today, with the help of some Python, image processing, and a bit of physics, we're gonna be writing an aimbot for this game. Now, you might not be familiar with this game, but for me it brings up a lot of nostalgia. I still remember the times of 2017 YouTube when this game was really popular because of the unique and cool weapons you get to shoot. The premise is as simple as it gets. There are two tanks on either side of the map that can move and shoot. Your goal is to destroy the enemy tank with the weapons you are given. I've been playing this game a fair bit and even gotten quite a ride at it, but there was always this idea in my head. Since the whole game revolves around setting up your shot correctly by adjusting the angle and the power, there surely must be a way to also calculate the perfect shot. So actually, about 2 years ago, as my first ever serious Python project, I wrote an aimbot for this game. I was really proud that I got it to work, but looking back at it, the code was painfully slow and poorly written. So today, I want to take another crack at this aimbot, with a lot more Python knowledge, and NumPy to help with efficiency. So how is this aimbot gonna work? Well, I'm not going to look into the game files, or basically try and write a hack for this game, mainly because I have no idea on how to do that, but I also think that calculating the trajectory just based off an image would be an interesting challenge. For that, we first need a way to get a screenshot of the game. So I quickly whipped up some code using the Python image library. But we're not actually interested in the whole image. The UI down here is not really relevant for us, so we can just crop it out. For this aimbot to work, we have two main goals to achieve. First, we have to determine the position of the tanks. For you and I, this might seem trivial, like one's here and the other one's over there. But for a computer, it won't necessarily be that easy. And then, from those positions, we have to calculate a path that will allow us to hit the enemy tank. Of course, we'll have to be a bit more accurate than my little doodle here, so let's just get started with the first one. Finding the tanks. A big part in why I chose this game to write an aimbot for is because of its very distinct color scheme. Our tank is a bright green, while the enemy tank is red. And everything takes place on a blue background, so the colors are as diverse as it gets. So we should be able to find our tanks by simply filtering the pixels by their colors. Computers represent colors in the RGB color space. Depending on how far along an axis one of these cubes is, it has more of that color. So for example, along this plane, the blue is 0. This means that all of these yellowish colors don't have any blue in them. But as we go along this axis, we add more and more blue to them. In this RGB coordinate system, we can now plot our colors. You can see where each color is positioned in the color space, and the size of the blob shows how much of that color we have in our screenshot. Obviously, we have a lot of blue, some light colors, and also some dark colors. And I can already see the blobs making up the red tank up here. They're luckily pretty distinct, but for the green tank it's already a bit more difficult. I for one can't really be sure where the tank ends and the background around it starts. This is because the RGB color space is not necessarily the best for filtering by hue, or what we would colloquially call the color. It's great for computers to work with, because the pixels in your screens consist of red, green and blue LEDs, but we'd rather switch to a different color space. Instead of tracking the red, green and blue values, we plot the colors by the hue, their saturation, and the value, or brightness if you wish. The transformation between the two spaces is not necessarily trivial, but it's a solved problem, so we're not gonna go into that. In any case, now we can filter by hue and only select pixels that are green enough. And then, just to be diligent, we can filter out really light and really dark pixels. And what we're left with is only green pixels. Of course, we can do the same now for the red tank too. To implement this in our code, we first need to convert the image into this HSV color space. Luckily, the image library can take care of that for us. I'll also reduce the size of the screenshot a bit, just to reduce the data load. Then I feed those pixels into this tank class. We give them an accepted color range they should look for. And using this method, they'll filter out any pixels that don't match their criteria. For red and green, I found these values work well for finding the tanks. As you can see, we've eliminated a lot of the irrelevant pixels in the image, so let's just focus on the areas around the tanks. Here we run into another issue though. Just filtering by hue is not enough. The colors actually mix a bit. The red tank also has a green health bar, and our tank shows this red turn indicator above. And both of them are still being detected by our algorithm. So we're detecting pixels of the same color, but that are spatially separated. If we ever want to expand this aimbot to also work with multiple tanks, friendly and hostile, we'll run into this issue as well. So we might as well handle it properly through k-means clustering. I admit this is a bit overkill for the simple case of 2 tanks, but as I said, it'll probably come in handy later on in this project. Instead of trying to detect multiple tanks on a battlefield, let's generalize this problem to points scattered on a coordinate system that we want to try to assign to groups. Again, you and I can do this quite easily. We see that these points probably belong together, so do those, and the remaining points also form a group. Makes sense, because I generated them by applying some random offset to those 3 mean points. But now imagine handing this task over to a computer. How would it go about finding the groups? In the beginning, it'll ask how many groups it should form, so in our case 3. And we'll need to give it some starting points. If we're smart about it, we'll pick some good points that are already close to the centers of those clusters. But in theory, we could also just pick them at random. Now the computer will pick a point, say this one, and check the distances to the mean points we chose earlier. We'll assign the point to the closest mean by coloring it accordingly. We'll repeat this for the next point, and the next, and so on. If we do this for every point, we'll see these Voronoi cells forming, where all the points within the colored regions will take on that color. As a last step, we calculate new means from the points in each region, and then update the position of the old means. And now it's just rinse and repeat. Sooner or later, the algorithm will converge, and the means won't move anymore. So indeed, the computer also found the correct clusters that we just eyeballed. In the proper code, I implemented the algorithm through NumPy to make it a bit faster, but the idea is still the same. And just for completeness, I'll say that this algorithm doesn't always work perfectly. If the data is messy, the results often depend on the initial choice of points. As you can see, we get different regions just because we started with other points. There are also methods to automatically determine the best number of clusters, so the k-value, but for us it'll be fixed or later come from user input. So with this algorithm, we can separate the green tank and its health bar, as well as the red tank and the turn indicator. Now all we gotta do is eliminate these stray pixels up here from the names and the health bar. For this, we'll just start from the bottom and look at what contiguous blob we can find. There is always some separation between the tank and what's above it, so we can just use it as a cutoff. And with that, we've successfully found our tanks. We'll use the means as the coordinates from which we'll calculate the shot. Again, the approach with the k-means clustering is a bit overkill at the moment. We could have just used the median point as a separator, but it made for some nice visuals in the video, and it future-proofs our code a bit. With the tank positions determined, we can move on to the part of the video I've been looking forward to the most: the physics behind the shot. Our intuition correctly tells us that the trajectory of the shot will look somewhat like this. So a path along this arch, where it first goes up and then curves back down. To be exact, it will travel along a ballistic trajectory, and since we don't have to deal with nasty stuff like air drag, calculating it is actually pretty simple. We can start by taking Newton's second law of motion, F equals ma. So if we apply a force, like for example gravity, on some object with a mass, it will accelerate. We're gonna split up this vector formula up into an x and a y component. Also, let's rewrite the accelerations as x and y double dot. Alright, let's talk forces. The only force our projectile experiences is gravity, and it's only acting downwards, so in y direction. In the x direction, we don't have any acting force, so we'll leave this entry at 0. But this is still just a formula for the acceleration. We want something for the position of the projectile. So we'll integrate both sides with respect to time and get a formula for the velocity. Here Vx and Vy are the initial velocities in the respective directions. If we integrate it again, we finally get something for the position. But wait, these are now in terms of a time t. We don't want to know when the projectile is gonna hit, we want to know where it's gonna hit. So we're just gonna rearrange the top formula and solve for t. This we can substitute in the y component, and finally get our desired equation of motion. One more thing I'll do is, instead of having the velocity in terms of an x and a y component, let's have it in terms of a magnitude and an angle, since that is closer to what we're given in the game. With a bit of trigonometry, we can substitute in these expressions for Vx and Vy. Now, in our current coordinate system, the y-axis is pointing up. But when dealing with images, the y-axis is usually flipped. So 0, 0 is the top left corner instead of the bottom left. Luckily, all this means for us is that we have to flip these two signs right here. So we're done here, right? Well, almost. Let's go through all the variables and have a quick check. x0 and y0 are the positions of our tank. That's what we spent the first part of the video finding. Theta is just the angle of the shot. It corresponds 1-to-1 with the one from the game. But what about G? Well, any good physicist or engineer will tell you that it's 9.81 here on Earth. But who says that gravity in the game is the same as it is on Earth? And even if it is, 9.81 refers to meters per second squared. But in terms of the game, it would make much more sense to work in pixels per second squared or pixels per frame squared. And what about the velocity v? The naive answer again would be that it's just the power value going from 0 to 100. But similar to g, the velocity has the units of meters per second, not something in pixels, so it can't be the power. What we can say is that it will definitely depend on the power, and we might already guess a linear dependence, but what it is exactly, we don't know yet. So to find out that relation, we're going to have to do some experimental fieldwork. First, I'll do something that might seem a bit strange. I'll just set g equal to 1 and ignore it from now on. This is actually something we do a lot in physics to make equations easier to deal with, and in this case we can neglect g completely. Then I'll rearrange the formula a bit. I'll just multiply out the square and combine like terms to get an expression like this. I know this looks really messy right now, and you really don't need to care about the exact expressions in here. Just keep in mind this characteristic polynomial form of our trajectory. ax squared plus bx plus c. Alright, that was the theory part. How can we bring in experimental data? Luckily, the game actually traces out the path our projectile took after each shot. So we can just use that as data to figure out our missing variable. For this, I wrote this simple app that allows me to take a screenshot and automatically label it. Then I went to MS Paint and traced out the path with a bright pink color. These colored pixels can then be detected by some code, and we can get their positions. So now we have a bunch of pixels on a grid. So how do we figure out the underlying polynomial? Now, if this data is perfect, then there is only one polynomial that will go through all of them. But in reality, you will usually have some error in your measurements, so there is no one polynomial that will fit exactly. But with polynomial regression, we can arguably find the best one. With this, we can match any data to a certain polynomial. And remember, the shape of our trajectory was exactly one of these polynomials, ax squared plus bx plus c. To find the coefficients, we'll first draw an arbitrary polynomial of this shape. I know this one doesn't fit at all, but it's a start. For this polynomial, we now measure how far it's off from our data points and sum it up in this mean squared error. If we move the coefficients around long enough, sooner or later we'll find the polynomial that has the least error. By this metric, it's the best estimate we have, so we can note down the coefficients. Regression is something we use a lot in physics. There, we usually have linear relationships, like voltage to current, or even radioactive decay if we plot it logarithmically. But really, this idea works for any polynomial. Obviously, the computer performing this regression is not wiggling around any graphs. The maths behind it tells us we just need to solve this matrix vector system of equations. And that we can just outsource to NumPy and not have to worry about it. Using this method of screenshotting, marking, and performing the polynomial regression, I made this table of A values for different powers and angles. Now, in and of itself, these A values don't really seem to have any connection if we plot them in this grid. But it's not the A we're interested in. If we think back to where it came from, we can use the A to calculate the velocity v. And if we plot that, we get our linear relation to the power just as expected. And we figure out all the necessary variables to describe the path our projectile will take. Without boring you too much with the maths behind it, we can use this trajectory to now determine the desired power and angle for the shot to go from our tank to the enemy tank. Actually, we're free to choose one of them. You see, there is more than one correct trajectory to hit the red tank. Infinitely many, to be exact. So as long as we adjust the power accordingly, we're free to choose the angles. Or the other way around, as a matter of fact. In my code, I'll provide the angles in increments of 10 degrees and calculate the necessary power. Now, obviously, we need to cap the power at 100. If the shot would require more, this angle is just too shallow, so we disregard it. Alright, I think that was enough explaining the code and explaining how this aimbot works. Let's actually put it to the test and showcase this aimbot. So for this I've loaded up a bot game here against an AI enemy. And on my second monitor right here I have VS Code up with the aimbot. So let's load into the game and try it out. So, okay, it's his turn to shoot first, that's fine. Now I'll move up a bit to be able to also showcase the more shallow angles. So if I go into my second monitor and type in pi main.py for run the aimbot, then it first actually gives us an image right here of what it sees. So here in yellow, that's our tank with the center point. And over there in blue, that's the enemy tank that it found, again with the center point. And right here we have our trajectories. Alright, so let's try one out. Let's do the one at 70, for example. So I set the angle to 70, and it tells me to set the power to 88. So I'll go up. And now we'll pick a weapon. Let's do, what do we do? Let's do the static link. And yeah, if it all worked out, we should hit it like dead on. There it goes, and yeah, you can see the path it took, and we actually hit him pretty well. Alright, so again, his turn. Now, I'll keep moving up to him, so again, we can see the more shallow angles. Oh, am I gonna be able to? Okay, I guess I'm stuck in this hole now. Oh, I'm actually... Maybe we'll see if it blocks my shot, whatever. Let's try it again. So I'll run the code again. It found the tanks, and it tells us... I'll try the one at 70 again. I think I almost went up too close to it. Oh, it actually went through. Okay. And again, we hit him pretty well. Now, there is actually some small things I changed from what I've shown in the video so far on how to calculate the trajectory, but I'll talk about it later. For now, let's continue with the showcase. So again, now let's do more shallow angle. Let's do 30 degrees. So right here, and it tells us to set the power to 51. So, and I'll go with the flower. And they, okay, well, I mean, we did hit him well, but with the flower, I guess you're supposed to hit him on the edge. But still, again, as you can see, it works pretty well. I'll run it again. And let's do 150 now. Just so you can see that it actually works at every angle. It's not just some select ones that I show you right here. And let's do a double zipper for that. 45, yeah. Now, there are actually some cases in which we don't hit the tank perfectly. Get the token. Now, there are multiple reasons for that, and to some extent I have it under control. One of that is some rounding errors, or also the orientation of the tank. So this tank is completely flat, or ours is tilted a bit. That changes a bit with, that messes a bit with the calculations and so on. But you know, all in all, it works pretty well. So let's do a really high angle. Let's do 80 degrees. Power 76. And for that, let's do the Python. Very, very fitting to our program. Let's do the Python. And there it goes. And again, just a perfect hit. Just a perfect hit. Then maybe let's try the Piñata to finish it off. So let's do the angle of, I guess 10 will be too shallow. Let's try, no, let's not mess around. Let's do 30 and power 54. And there it goes. Hits him dead on again, bounces a bit, but I think it doesn't make a difference. And he's dead. So yeah, I'm really happy with this aimbot. It's really fun actually to try it out, to see like how it actually always hits perfectly. So yeah, I think I'll share my final thoughts, some other comments that came up during recording this video, during refining the code. And yeah, this will be it. So I think it's safe to say that we've achieved our goal of writing a working aimbot. Now, to address the things I just mentioned during the gameplay. The one change I made is that I don't use the center of our tank as the starting point for the shot, but I found that it should rather be the end of the gun barrel. So with some simple trigonometry, we can adjust our starting position a bit. Then there is the issue of rounding. Since we can only set the power to integer numbers, our code rounds the calculated power up or down. And sometimes when it's right in between two values, this could result in missing a shot, or at least be a bit off. I guess the simple fix would be to just test all possible angles and pick out, say, the top 10 that have the least rounding error. So that's definitely an improvement we could make. Other than that, I still have the plan to make it compatible with multiple enemies at some point. Now that we have the maths and the clustering algorithm, it probably shouldn't be that hard to get it to work. But for now I'm pretty happy with this, and I'll call this project done for today. So thank you guys for watching, and see you next time.